occurred at NCAR in Boulder, Colorado, and I was looking at the NAO and the PDO and how they're related to black carbon in the Arctic. We wanted to look at this because previously people have found that the NAO helped determine the amount of black carbon reached in the Arctic from Europe, but no one had really looked at the PDO and thought about black carbon transport from Asia being influenced by the PDO. So we took 160 years of model output from CamChem and broke it down and looked at it and tried to figure out, does the PDO also have an influence on black carbon? And we looked at it many different ways. Ultimately, we found that individually the PDO does not have much of an influence. But when you look at the PDO and the NAO together, that when the PDO was negative, the NAO was actually even more related to the deposition of black carbon in the Arctic. So that we saw, by looking at the changes in deposition, that most of the changes occurring under these two regimes working together were occurring in the wet deposition field, which is somewhat unusual because most of the deposition in the Arctic at times is actually due to dry deposition. So when I looked at this to see what was causing the changes in wet deposition, we saw an interesting pattern where the precipitation signals due to the NAO and PDO were co-occurring in certain times in certain places to lead to overall greater precipitation and greater wet deposition. By looking at this data from the model, we were able to intuit that future studies of black carbon transport into the Arctic should definitely be thinking about these large-scale oscillations and be thinking about them as they work together and not just as they look individually.